Now, and this is the result that I showed you before in the introduction. We have an excess power of the order of 1 watt increasing to a value of 3.5 watts. This time here, the total power of the system was stepped from 10 watts to 12 watts. And this effect represents as much as 28% of the input power. Just to see what sort of effects we're talking about, however, I show you the total power here and the excess power. So the effect is observable. The measurement uncertainty is defined and small with respect to this observation, but we're still looking in this case at an effect which is only, 20–30% of the total input power. I want to give you at least one example of other than baseline power observation. As I said, we've observed this sort of effect on something like 38 occasions. We started to add boron for good reasons, and if anybody asks later, I can give you the reasons for it. First thing we observed in cells to which boron is added to the electrolyte is boric acid. The boron goes into the metal and affects the resistance ratio. So here we have a time in which we first stepped the current down to low values, reversed the current. The cell voltage follows this profile on the reference voltage. The interesting thing is that instead of the resistance ratio going back over its, so the resistance ratio versus loading curve look like this. As we strip the cell, we expect to see the resistance go over its maximum and come back down the other side. Instead of doing so, in the case of cells to which boron has been added, we see 2 maxima during the stripping and 2 maxima again during the reload. This value, the deuterium, should be about 2. You observe that in the cells to which boron is added, that value is 4. This is still hard for us to explain. It's nevertheless a very well reproduced observation. More interesting still, perhaps, and here we show data for the raw measurements of 2 RTDs and 2 thermistors. This is the same current reversal that I showed you before, followed by a current ramp. The excess power, in fact, unbeknownst to us, had initiated at low current. We were starting to observe excess powers of the order of 0.3 or 0.4 watts before the current reversal. During the period of the stripping, the excess power actually comes back down towards 0, but restores itself. In an attempt to increase the excess power observation, we ramped the current, and the excess power is very little correlated to the current density in this case. This is one of the observations that I described as a burst, being uncorrelated to the parameters that we have ourselves under control. We have data from 2 RTDs and 2 thermistors. The 2 thermistors do in fact show some sort of systematic variation, but apart from that, that small glitch here, all 4 temperature sensors see essentially the same result, and the excess power calculations are the same. Power input at that stage? In fact, I'll get to that point on the next slide. This was a time in which we had prepared the calorimeter to be ramped. The calorimeter was set at 14 watts of total power, whereas there was very little electrochemical power because the electrochemical current was only 0.1 of an amp. If we normalize the observation in this case to the total power, however, because we had 13.7 watts of heater and 0.3 watts of electrochemistry, the normalization of the excess power observation to total power is a small percentage, and here we have the measurement uncertainty reflected. To observe the effect of the heater, we stepped the heater down at this point, which did not affect the excess power, but affects its percentage, of course. So normalized to the total input power, have at most a 12% observation. You would normalize to the total power if you thought that the effect had something to do with a heater or with some form of artifact. In this particular case, if you normalize to the electrochemical input power, obviously we'll get a much larger effect. And we have an effect, something like 250% of the electrochemical input power, with the uncertainty now expressed in terms of a percentage of the electrical input power is a larger number, but nevertheless a small number compared to the observation. I wanted to finish up here with our summary of observations. Unfortunately, there's a lot more that I really need to say. One of the things which I wanted to show you is from one of the more recent cells we're able to observe the correlation with statistical significance between the excess power observation expressed in terms of watts per cc and the loading. And I fitted three functions to this. So excess power, loading determined by the resistance ratio. I fitted three functions, and you can clearly not distinguish between them. An asymptotic function, asymptotic to a loading limit of 1, which you might expect if the parameter that we're observing is correlated to the activity of deuterium in the lattice. An exponential function, which you might expect if the observation of excess power is correlated to the population of a higher energy state, such as occupation of the tetrahedral sites in a Boltzmann distribution. And a parabolic function, which you might expect if the excess power observations are somehow correlated to two atomic interactions, the possibility of two species getting together above a critical threshold. The data are simply not good enough to distinguish between them, but there's clearly a correlation between the excess power observed and the loading. And I'll just summarize our observations from these cells, and we'll be happy to provide experimental support for some of the conclusions which I haven't yet given you. Basically, we have observed more than 350% excess power in a burst mode as correlated to electrochemical input power. We observe 5 to 50% baseline effects with, in terms of a measurement uncertainty, somewhere between 8 and 90 sigma observations. We observe these effects in each instance of excess power observation in the range 0.1 to 1 megajoule, and that's between 10 and 100 times the sum of all of the chemical reactions that, the known chemical reactions that may occur in the cell, given the chemical inventory that we have. We observe more than 45 megajoules per mole of palladium, corresponding to something like 450 eV per atom. 200 watts per cc of excess power for an experiment which has a small number of cc's. Internal repeatability correlated strongly with the deuterium loading. Experimental reproducibility in the experimental sequence P12 to P17, one of which was a light water cell. All of those experiments produced excess power when performed similarly to the prototype experiment P12. We never observed negative excess. If you were thinking of certain classes of systematic error that might occur, you might think that they would occur as equally in the positive direction as in the negative direction. We never observed negative departures from the thermal balance of the system except under transient conditions. Excess power has not been observed with light water, and light water has been observed to terminate an excess power observation, and observations were being made in heavy water cells. And we observe excess asynchronously in series cells, suggesting that measurement errors due to drift in the multimeter are not themselves sources of the error. There's a reproducible pattern. We don't observe excess before a certain initiation time. In general, the excess increases with time until the deuterium to palladium ratio is lost, and we think this is a feature of contamination of the surface with undesirable species so that we can no longer achieve the electrochemical conditions necessary to achieve the loading. We've observed excess heat, similar characteristics in two different types of calorimetric cells, two different types of calorimeter. And in conclusion, we presently are unable to account for the observed excess temperatures by any artifact that we have considered. And you cannot account for the measured excess heat by any chemical or mechanical process with which we are aware.